All right, welcome to the second video of two videos on Gauss's law. So the first video we introduced electric flux, talked about symmetry, and talked about Gauss's law right here. So just to remind you that Gauss's law, shown here, relates the electric flux that's going through the boundary of a closed surface or Gaussian surface, real or imaginary surface. Gauss's law relates the electric flux through that surface to the net enclosed charge inside. So your book calls this Q in. That's not the total number of charges inside, it's the net charge. So you might see this as Q in, you might see this as Q net, you might see this as Q enclosed, ENC. Other books will write ENC for enclosed charge. All of those mean the same thing, the net charge on the inside of your closed surface, and you can ignore all of the charges on the outside of that surface because they have no net contribution to the flux through the closed surface. And remember that flux is positive if electric field lines are leaving the closed surface, and flux is negative if it's entering the surface. So in other words, this dA vector points in the normal direction outwards, the outwards normal to the surface. So you could try this problem, maybe just stop the video and just to see if you can apply Gauss's law directly to this. So pause it now for a couple of seconds. I'll wait a couple of seconds. Okay, so we're asked to rank the electric fluxes, and the electric flux is just linearly proportional to the net charge inside. So it looks like the net charge looks like B and E have the biggest charge. B is equal to E. And those are bigger than the flux that's going through A, C, and D, which all have a single Q there. So it looks like B and E have the most flux. Keep in mind, this has nothing to do with the size of that closed surface, right? The fact that B and E have closed spherical shells that have different radii, that's irrelevant because the only charge that's inside both of these is the same. So right here. So in other words, the right-hand side is saying that these two are the same thing. So the flux is the same for these two. It doesn't matter that, so like in this integral of E dot dA, what this is saying is that the electric field here is stronger, but there's less area versus E in picture E. In picture E, the electric field is less, but the area is bigger. So like if the radius of this spherical shell was twice as big as that in B, that means the electric field is 1/4 as big, but there's 4 times the area over which it's spread. And those two things are exactly canceling out, which makes the overall flux equal for the two. Okay. So this next section is really getting at why we care about Gauss's law. And now we're going to start using symmetry and combine with Gauss's law to solve for the electric field for symmetric charge distributions. So if your charge distribution is one of those 3 symmetric cases that we talked about in the previous video, remember we have spherical symmetry, cylindrical symmetry, and planar symmetry. If you have one of those 3 types of symmetry, you can use Gauss's law to calculate the electric field due to that charge distribution. Okay, and that's what's done in the next few examples. So, these quote unquote examples are more like proofs. These are the examples that are in every book on Gauss's law. You have to know these. You have to know how to do these yourself. You basically have to be able to reproduce this and understand every step of this. These are more important than just normal example problems. Our example problem is actually just using the result of these example problems because these example problems are so important. They're basically like the proofs, and you have to know the main results. So yeah, I would have them written on a cheat sheet, or you should just have the main results known. For the 3 cases, they're basically 3 different formulas, and you have to know those formulas. So there's 4 examples here. This is outside and inside a spherical charge, so that's spherical symmetry for the first 2. And then your book does cylindrical symmetry for this example, and then planar symmetry for this last example. So some important results from each one of these. So let me talk about each of these in more detail. Okay, so this example So the next two examples are going to focus on a spherical shell of charge. So this is a 2D cross section. There's a uniform. So in other words, there's going to be a surface charge density that's constant over the surface of a spherical shell. So this is a 2D cross section, but actually this is a spherical shell. You have to imagine that it's a 3D thing, and there's a total charge Q. So maybe so this would be the total charge on the sphere divided by the total area of the sphere, which would be 4 pi r squared. And capital R will be the radius of this thing. So this example looks at points that are outside the sphere. So say I want to know the electric field right here for a point outside the sphere. And then the next example, example 24.4, looks at lowercase r less than capital R. So a point inside the sphere, what's the electric field? And to ruin the surprise, or to sum up both of these examples, the electric field here outside the sphere is the same as though all that charge were just located at the very center of the sphere, the spherical shell. So that you have all this charge. If all that charge were just at the very center, it produces the same electric field right here as this complicated object. And we're going to prove that with Gauss's law. For a point inside the spherical shell, to sum up the result of the next example, the electric field is 0. So for a point on the inside, there's going to be electric field contributions that point one way. So like these charges are going to create an electric field that points this way. These charges are going to create an electric field that points this way. And those contributions actually exactly cancel, which is kind of an amazing thing. So how do we use Gauss's law to prove this result? Okay. So there's a sequence of steps that go into the logic of this. Okay, so the first step is you know the direction of the answer. The direction of the answer from the symmetry of the charge distribution. So because eta is constant, because the surface charge density is constant, there's spherical symmetry, and the electric field, if it exists, has to point radially. So that's one thing. So the first step, use symmetry to deduce that the electric field points in the radial direction for any spherical symmetry. The next thing is the step 2 is to draw a draw a Gaussian surface that is a spherical shell that goes through the point of interest. So if we want to know the electric field here at this point, we're going to surround this thing with a spherical shell that's not a real thing. It's an imaginary mathematical surface that's just going to help us. So this is our Gaussian surface. Our Gaussian surface is a spherical shell surrounding the charge distribution in this case. In this case, the charge distribution is on the inside, and the point is on the surface. So the Gaussian surface is of radius r. So it's going through the point that we actually want to know the electric field at. And that's what's drawn right here. So the actual charges are right here, but the Gaussian surface is what's drawn right there. And we're going to apply Gauss's law to this Gaussian surface. So step 2 was to draw that Gaussian surface. So step 3 is to apply Gauss's law and simplify. So Gauss's law says exactly this, what I just circled there. Maybe I should switch to a different color at this point. So Gauss's law is this right here. And because of all the symmetry involved, this part right here simplifies a lot. So the fact that we have spherical symmetry means that the electric field points radially outwards. The electric field is some value. So the electric field is some value that we don't know what it is. And it can actually depend on how far away that point is away from the center, right? So it's some function of r. We don't know what that is, but we do know that it points in the radial direction. So it's some function of r, but we definitely know it points radially outwards. The dA, so in other words, for every piece on this Gaussian surface, there's a little patch of area, and the area vector is going to point in the outwards normal. So the area, remember the outwards normal direction is normal to the surface and pointing out of our closed surface. And here it's no matter what part of the Gaussian surface we have, it's going to point in the same direction as the electric field. And that's what they drew right here. So that dot product simplifies, and it's just E times dA And the electric field magnitude over the whole Gaussian surface is constant. It's the same value everywhere, again, because of the spherical symmetry. So we're going to say the word symmetry over and over again. So it's integral of E times dA, and we can take, so we're integrating over the spherical shell over our Gaussian surface, which looks really intimidating, but the fact that our Gaussian surface all has the same radius means that E as a function of R is actually a constant, because lowercase r is constant over this whole integral. We're integrating over the surface. So we can take it out of the integral. And the whole point of all this is so that we could write this down. It's the electric field times the area of that sphere. So there's a lot of symmetry. So it's because of the symmetry of everything going on that we can actually make this replacement. Okay, and then your book just plugs in the area of a sphere is 4 pi r squared times the electric field. So that's the left-hand side. The right-hand side is the total charge of our sphere, of our spherical shell. So the total enclosed charge is just Q. So that gives us this. And then moving everything over, so solving for E, moving everything over to the right-hand side, we get that the electric field outside the sphere is the same as a point charge located at the origin. So this is KQ over R squared, which should look really familiar. So what we've proven is that the electric field outside a spherical shell of charge is the same as though all that charge were just located at the center. You'll notice that the next example is actually exactly the same steps. There's a lot of the same steps. The left-hand side of this is exactly the same, even if our Gaussian surface was inside the shell. So the left-hand side, again, you use symmetry to simplify it to here. The only difference is the right-hand side is 0 in this case. Oh, this is a, sorry, this is a uniformly charged sphere. This isn't a spherical shell. I said that the second example would be 0, but so this is outside a sphere of charge. If it was inside a sphere of charge, you would get 0. So let me put, this result is actually important. Inside a shell of charge, spherical shell, SHEL, the electric field is 0. So outside it acts like a point charge, inside it has no overall electric field. Okay, so this next example, actually has charge spread out over a whole interior. And so what this means is that, so the left-hand side here is exactly the same. So again, so the left-hand side is E times the area of our Gaussian surface, right? So that's this step right here, 4 pi lowercase r squared E. But in this example, the right-hand side is a little bit more complicated. So if our Gaussian surface, which has radius lowercase r, is inside the whole sphere of charge, radius capital R, then the enclosed charge is some fraction of the total amount of the charge of the sphere. What fraction? Well, it turns out it's lowercase r cubed divided by capital R cubed times the total charge. Okay, so it's the ratio of the two volumes. And so when you plug that into Gauss's law and then get the final result, you get that the electric field actually increases linearly proportional to R until you get to a maximum value that's the value of the electric field right at the surface, which is, and then afterward it's KQ over R squared. So that's spherical symmetry. Cylindrical symmetry, we have to shift gears now. So this new example, we have to think about an infinite line charge. And the Gaussian surface that we're going to choose is not going to be a sphere at all, because that's not the symmetry involved here. What we're going to do is we're going to choose a cylinder. So we know the electric field of an infinite line charge is pointing radially away. Different r hat now. By the way, we use r hat for cylindrical symmetry and spherical symmetry, but they mean something else, right? Here, r hat is pointing not away from an origin, but away from that line. So these are the r hat directions. That's the direction of the electric field. We're going to surround our line charge with a cylindrical shell. So in other words, the walls of the cylinder and then the end caps, but that's it. And when you simplify Gauss's law, again, you're using the symmetry to simplify that the flux, which is only going through the walls of the cylinder, not through the end caps. But the flux is the electric field at some radius, lowercase r, times the area of the walls of the cylinder, which is 2 pi r times the length of your cylinder. So a capital L is the length of your Gaussian cylinder, which is something you invent in order to solve the problem. But it's actually going to cancel out. Notice how the final answer isn't going to depend on capital L. So capital L, the amount of flux that's going through your cylinder is proportional to L, but so is the enclosed charge. The enclosed charge is lambda times L. That's how much of this rod is contained in the cylinder, capital L. And when you multiply with a linear charge density, you get the total enclosed charge. So you plug this into the right-hand side of Gauss's law, and you plug in this in the left-hand side of Gauss's law, and you simplify and solve for the electric field, and you get this, which is the main result for this type of symmetry. So the electric field is proportional to 1 over r. If you double the distance away from the line charge, you have the electric field strength, which we saw before in last chapter, but now we've proven this much more easily. And this shows the strength of Gauss's law as well. This is a lot easier than actually doing an integral from negative infinity to infinity. The last type of symmetry is a plane of charge. And this, for this, you're going to choose a Gaussian surface that, here they chose a cylinder, but it doesn't actually have to be a cylinder. Some books call this like a Gaussian pillbox. This could have any funky shape. And really, you're just having the shape that's it has to be the same funky shape on both sides. but it's sort of straddling the surface. It's kind of, the surface is piercing through your funky shape. So your surface has area A. And again, the electric field, again, from symmetry, you know that the electric field has to point away from the plane of charge. So the flux that's going through your Gaussian surface, well, there's two contributions. There's one through this end cap, and there's one through this end cap. So the flux is, there's two areas. There's 2A, the two end caps. If each end cap has area A, it's 2A times the electric field at maybe some radius. So we're thinking that the electric field could depend on that distance. So E maybe is a function of R. And then the enclosed charge is eta, charge per unit area times the area. So eta times A. And then what you get here is that the electric field from the plane of charge is actually a constant, which is surprising. So in other words, if you're here some distance away from the plane of charge, or if you're twice as far away, it's actually the same electric field. It's actually the same amount. It doesn't die down like it does for the other two cases. This is a surprising result as well. The last section, so we're actually able to do the example problem, but let me finish up the text here. The text then talks about conductors. So conductors are pieces of metal. If they're in equilibrium, then that means that the electric field has to be 0 in the metal. So that doesn't depend on Gauss's law at all. But metal have, a piece of metal or a conductor has an infinite number of mobile charge carriers. So in other words, there's an electron that's just hanging out here and it's free to go wherever it wants. If there's a free electron in the middle of the metal and there was a non-zero electric field, it would move. So the fact that we're in equilibrium, electrostatic equilibrium, means that there's no electric field in the metal. That's one property of the conductor. So that property, combined with Gauss's law, leads to a bunch of conclusions. And I guess there's no list of these conclusions, but that they're bold-faced right here. So, well, so this isn't from Gauss's law. This is just the fact that you have a conductor and an infinite number of mobile charge carriers. Same with that. But the actual electric field at the surface, you can use Gauss's law, again, with the same kind of Gaussian surface that we used for this example. But this time, for a conductor, if the electric field is 0 on one side, then that means the total flux, all of that flux has to go through one of the end caps. And so the electric field is actually 8 over epsilon naught, not 8 over 2 epsilon naught, like in the previous example. Another consequence is that if you have a hole or a cavity in a conductor, you can use Gauss's law. So that what the author did was draw a Gaussian surface here. And here we definitely know that there's no electric flux going through the Gaussian surface because the Gaussian surface is wholly contained within the metal. So there's no flux going through it. And by Gauss's law, that means there's no enclosed charge. So if there's no charges in the cavity and there's none on the metal, there have to be none on the inner surface. Kind of a slick argument, but worth thinking about. And then your book talks about screening and Faraday cages as well. We'll talk about this a little bit more in class. To prevent the video from going too long, let's go over to the example now. So this is using, okay, so the problem is that you have an infinite sheet of charge and an infinite line charge, and they're separated by a distance d. So given that both of these are positive, where is the electric field 0? So first of all, the answer has to, if it exists, has to be in this region right here. Okay, like above, there's both of the electric field contributions are up, and below, both of the electric field contributions are down. So it's only up here that the electric field contribution from the rod is up, and from the infinite sheet of charge, it's down. Right, so the answer has to be somewhere in between there. Suppose we're a distance r away from the infinite line charge. Right? The electric field there is going to be a sum of two contributions. So let's call this point P. The electric field at point P is a sum of two contributions, and let's call this the z direction. So there's a contribution in the positive z direction because of the line charge, and that's, if you remember from the example problem, this is lambda over 2 pi epsilon naught times 1 over r in the z hat. And then there's also a contribution, so I'm going to hold off on the sign right here. There's a contribution that's eta, so let's put plus or minus here, eta over 2 epsilon naught in the minus z direction. So you could put plus this in the negative z hat direction. So in other words, this is from the rod, and this is from the plane of charge. The sum of those two is the total electric field. So if we're going to require that the electric field is 0, so we can set that equal to 0. Looks like there's a factor of 2 and epsilon naught that's common to both of them. So 0 equals lambda over pi times 1 over r minus eta. Or in other words, r is lambda over pi eta. So we don't, when we started this problem, we didn't know the values of lambda and eta. So this r could be greater than d, but that would give us a contradiction. So this is the answer if this value is less than d. If it's less than d, then it makes sense. Then this point is in the region in between these two. If lambda over pi times eta were greater than d, then there's no answer. So if that's the case, then the electric field contribution from the rod is always greater than the contribution from the infinite plane in this region. And so there would be no points where the electric field could be 0. Okay, a lot to digest. Good luck.